In organic chemistry lesson 3, we get to talk about hybrid orbitals, so we finally get to learn something new. We talked about ionic and covalent bonding already, and we've exhausted to death the idea that carbon has a 1s energy level and then a 2s energy level, and then you're going to have the p orbitals, right? You got a p orbital and a p orbital and a p orbital like that in your second energy level. You should know this. You should understand this. But today I want to talk about what happens when we add 1, 2, 3, 4 electrons. No longer are we going to have p orbitals. In fact, let's bring up the diagram for carbon. Here's my carbon. Here's carbon's second energy level. There's an s orbital. That's my lithium and beryllium, right? But then carbon has more electrons, and it begins to fill the potential space here. The potential space for these p orbitals. We don't know which of these p orbitals are electrons in, but let's just decide. Let's decide together what it's going to be for the example case here. I'm going to say that carbon filled one orbital here, and maybe one orbital here, and he still has carbon's going to be a she today. She still has 2 electrons in an s orbital here like this. So there's still these potential orbitals, and maybe the electrons oscillate between all of them, but there's a lot of open orbital space here in carbon, a lot of it. So what happens if I want to bring some hydrogens along and appreciate 1, 2, 3, 4 more electrons to finish the second energy level? Let's bring a hydrogen in here. Hydrogen has a 1s orbital. Well, I'm going to have carbon's p orbital reach out and connect their soap bubbles and create a new idea here, like this. And carbon's electron, we'll make it pink for hers and blue for his. It's going to reach out like that. And then maybe we have another one down here. Let's do 4 hydrogens, right? Carbon has room for 4 of them. Just do it real quick here. Carbon, of course, taking up a lot more space than hydrogen. Their orbitals are going to overlap like this. You know this. That's how chemical bonds work. So carbon's going to donate her 4 available electrons. Look at the second energy level. She has 4 available electrons. But something else is happening here too. Notice that this s orbital is being ignored. We're just kind of assuming it's all p orbitals, which is not correct. But for this demo, let's take a quick peek here. Carbon has the 8 electrons necessary to complete the second energy level, and hydrogen has the 2 electrons necessary to complete the second energy level, so this covalent system is really nice. But the problem is these electrons know each other exist. They don't want to be close together, and there's more electrons nearby than there used to be. And these protons here, they don't want to be near each other either. So even though all of these electrons really want to get to this center nucleus where there's 6 protons, they're really interested in being close to that center. These 4 corners don't want to be by each other. And this isn't a 2-dimensional system. It's a 3-dimensional system, and in 3 dimensions, the 4 points that are closest to something but farthest away from each other is in a tetrahedron like this, with your center connecting them like this. 1, 2, 3, 4. Let's use a different color. It's hard to see that. 1, 2, 3, 4. So when you look at carbon, you're going to see that, like that, and that, and that. That is kind of the shape that it makes. It's called a tetrahedral shape. Imagine that. But as far as we're concerned, all you need to know is that they form bond angles in 3-dimensional space that encourage hydrogen to be as far apart from other hydrogen as possible. And as a consequence, with this s orbital being totally taken away, what was an s orbital here and a couple p orbitals are now being used to form these bonds. And you don't get an even split. What used to be an s orbital and then next to it, working alongside it, these were all potential electron spaces, was a p orbital. This has become something new. Now you get a fat merged hybrid version of a p orbital with a tiny little anti-bonding node on the other side like that. This is what it actually looks like. Because we know where the electrons are. They're here. They're here. They're not behind the carbon. They're not, when you take this orbital here that's making this bonded space, the one behind it, the potential there is almost gone now. That's this back half here. It's not there. We know where the electrons are. So, in fact, I have a diagram of this as well. Let's look at what the new orbit looks like. Let's remove this here. My art isn't the best, but I actually think it's helpful because I don't want you to be overwhelmed by information. I want my stupid art to be used. Look at this shape here. Now that should make total sense to us now, because if my hydrogen is right here, we know the electrons are in this orbital. Here's my hydrogen here. There's one way in the back out there. He's just far away. Yeah. We know the electrons want to be right in here. So look at the back side of this orbital. Very little opportunity for electrons to be there. They don't want to be there, especially since this orbital right here is busy with their electrons. See, if I have a hydrogen bonded here, why would my electron be found behind the nucleus on the other side? Very unlikely. So this orbital has a name. It's called SP3. I'm sure you see it right here. And the reason we call it that, if you want to think about it in simple terms, is that we have an s orbital and we have 3 p orbitals, and it's being merged instead into 4 equal shaped balloons here. So this is our SP3, like this. And any time you have a tetrahedral bonding, well, that's 4 bonds. You're going to get this SP3 shape. And that's all you need to know for hybrid orbitals today, is that these soap bubbles pop into each other and they change in shape, and you end up creating a new set of atomic orbitals from this bonded group. So when you see methane drawn in 2D, which they absolutely will draw like this. In fact, we'll even take out the C, because in OChem we don't use C anymore. We just assume that if you see a lack of a chemical name, then you must just know that that's carbon. So I'm going to draw it like this. All you're going to see written is this. And it is your job to look at this and go, ah, there's a carbon in the middle, and I see 1, 2, 3, 4 bonds. That is going to be SP3 orbitals. The shape of the orbital between carbon and hydrogen is going to be this asymmetrical hybridized orbital, hybrid orbital, and they're all going to be the same. Why wouldn't they be the same? They're all bonding to the same kind of atom, and they're all bonding for the same reason with the same energy amount. You should be able to draw this all day long and understand that this lack of symmetry is very important, and that it exists because we now know where the electrons are. They're between the hydrogens and the carbons. I've beaten it to death, so you should understand now hybrid orbitals, at least the SP3 fashion. In the next video, we'll talk about a couple of the other shapes that this produces. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.